too. So I'm happy you guys made it. We're just getting started, so you haven't missed anything yet. Just go ahead and open up that Google Doc and mark a green check once you have the file. And every assignment that you do in physics, you should use the template. And the reason I say this is because I tried to add extra hints and videos that will help you along the way. So if you didn't already see this template for this assignment, these kind of videos would have been an option. But today, if you're able to stay for the whole session, we're just going to knock out the whole assignment right here. If you do need to go back to any parts of this, and I have a screenshot, I think, nope, that's too far, right here. This template happens to have kind of a video for every step. So if you did need to look back at any of this, you can do that. And for future assignments, make sure you're scrolling down the announcement page. There'll be a template for any of our lab assignments, and I try to embed the videos right there within the directions. So going back to kind of the key ideas here, there's really three spots that make this assignment tricky. The first one is reading the vernier caliper. I'm imagining most of you probably don't have a caliper at home, so it's one of those things where you're trying to learn a tool that you can't even like put in your hands and use. So it is a little foreign and a little tricky, but once you see the pattern, I think it's not as bad as it seems. Then the next kind of key piece is doing the calculation part of what the lab's asking, and I don't know that the lesson does a good enough job of really explaining what's happening there, so we'll dive into that. And then kind of overall, the part of the reason for this assignment is looking at this idea of direct measurement and indirect measurement. So we're going to go kind of out of order here and start with direct measurement and indirect measurement, just so we have that vocab out of the way. So here's a set of 4 pictures, and I just guess maybe based on the sound of these terms, direct measurement, indirect measurement, I want you to kind of take a guess at what you think these would be. You can use the writing tool to either write a D or an I in each one of these boxes. Maybe just write right on the pictures. This first one here, we have a baby that's born, nice little cute birth announcement photo there where the baby's being weighed. And it weighs about 7.5 pounds. Would that be a direct measurement, or do you think that would be an indirect measurement? Go ahead and place the letter that you think somewhere in that box. And then over here we have, I do this with my kids, we measure against the front door and we make a little line as they're growing. Then down at the bottom here, we have the mass and the radius of the Earth. So those are really large numbers. And we want to think about, well, is that an indirect measurement or is that a direct measurement? And then if we really zoomed into water, one little molecule of water, which we can't really see with the naked eye, has a super tiny mass. And you guys did a great job. So I think without even maybe thinking about it, you probably already have a little bit of comfort with this idea of direct measurement and indirect measurement. So part of the assignment will be to kind of put that into words. What's really happening when we have a direct measurement? And one of the things that I would suggest that you kind of think about and remind yourself of is that when we're measuring directly, we have that thing right in front of us that we're trying to measure. The baby's right there, the kid's right there. We're not extremely far away or not within reach of that object. Whereas with the sun and the molecule, one is just way so tiny that we really don't have a tool to measure that directly, and the other is large and far away. So there's reasons where we'd probably prefer indirect due to the fact that it's just not possible to do a direct measurement. And realizing those two differences are going to be 2 of your questions. So what I will point out in your assignment, let me scroll over to the question section. 1D is simply asking you to define what indirect means. So we don't have to do that right now, but that's all they're going to be asking you to do there. What really is involved in an indirect measurement? And one of the things that we probably should recognize that I didn't mention from that picture slide is that to get those answers for the mass of the molecule or the size of the sun, we really have to do some calculation. We're collecting other data for the sun, some astronomy data, to really predict the size of the sun. So we're using a little bit of calculation there. Oh, that's strange. I wonder if the file got messed up. Let me look at this is 1D. Okay, yeah, go ahead and just fix it. I'm not sure why it did that, but yeah, go ahead and fix that. So 1D is indirect, and then you'll see later 2B is the one that should say direct. So all you're really doing there is summarizing in your own words what the difference is between those two. So I don't think that's too bad, right? We can handle that. Now what we want to do is really see what that looks like. What does a indirect process really look like? So the way we'll do that is by using this caliper in this lab. So I'm going to check off the terms. We're pretty good with those. And let's dive into this caliper. So this is a picture of a caliper, and it's kind of zoomed in. But what I think makes it easier to understand this caliper is what's really in the background that we can't see. This piece up here that I'm putting a star on, that little strip, is connected to this piece down here. You can kind of see a dividing line there and here. So when let's say instead of an M&M, I had a whole candy bar and I wanted to measure the length of that candy bar, I would be sliding that prong, this one right here, I would actually be sliding it open wider, and this piece up here would move along with it. So I think realizing that helps make a little more sense of this. And then the other thing to notice is that the way we're measuring here is not what we're typically used to. If I, look for a ruler around my house and I want to measure, let's say, the size of a pencil, I just look to the end of the pencil and I measure it and I'm done. This takes a little extra work. What we don't want to do is measure to any of these edges. I think this is the common misconception. Our eye kind of just goes to the edge, and we try to read off of one of those. All of those are wrong. With a caliper, instead, it's specifically designed to be measured from the 0 mark. So there'll be what we call a vernier scale, the strip. Sometimes it's at the top, sometimes it's at the bottom, or sometimes it's in both places. Wherever that happens to be, and for ours, we're using this one up here, we're measuring to this point, to that 0. And the way I like to look at it is to, actually, if I could, move this M&M. So I can't, of course, since this is a picture. So I'm just going to copy over this M&M, and I'll make it yellow there. So that would be the M&M that's sitting there. What I can do is bring it up to where these zeros are. And notice the width of that M&M goes from the 0 that's over here to the 0 I want to measure to. So we're really just transposing that length up here. And I think noticing that makes this make a little bit more sense. So now that I've said that, let's look at how we would read this. The first step, of course, is to put the object there. These are called the jaws of the caliper. Then we're going to get a whole number from the 0 spot. And the way you want to approach it is kind of think of maybe if you were a tiny little ant that was crawling on this vernier scale. This 0 is your finish line, and that's as far as you can go. So we want to read basically how far you've made it. So this one, I'm just going to be counting up from 0. So here's 1, 2, 3, 4. So I didn't quite pass the 5. I can't count that. So my first digit here would be a 4. So everybody see where I'm getting the 4 from. And I'm going to erase the checks. Give me a green check if you see where that 4 is coming from. Okay, so far so good. So we'll do this a couple more times, and I know one practice isn't enough, so I have some more of these. So let's just keep going with this one, and then we'll revisit a couple more here. Now this next part is really impressive when you kind of look at the bigger picture here. Vernier designed this so that we can get an extra digit here. Now in everyday life, if I just am measuring something, I'm probably going to say, okay, that's close enough to 5, and I'd be done measuring. Here, we're trying to be a little more scientific and really be more certain as to what this digit is. The way we do this is to look at those little dashes that come after the 0. And this piece is called the vernier scale. This is what makes this ruler special. So this first little dash is 0.1, and then we keep going, 0.2, 0.3, 0.4, 0.5, and so on. What I'm looking for is the first one of those dashes that matches up perfectly with the line under it. So notice point 1, it doesn't match. It's not lined up. Point 2 doesn't match either. And I'm going to do this for each and every one. 3 is no good, 4 is no good, 5 doesn't work, 6 doesn't work, 7 doesn't work. 8's getting better, but look at point 9. It's lined up perfectly with the line under it. And it seems a little strange at first, but it's only going to work for one of those. And the one that it matches up to is the digit that we want. So this one would be a 9. So my answer here would be 4.9 millimeters. Now, like I said earlier, 5 would have been close enough if we were doing something informal. But in science, there are times where that 1/10 is really going to make a big difference in what we're doing. And that's really the intention here of being more precise with our reading. So hopefully that's soaking in and making some sense. Let's try another one and see how you guys feel about this one. So again, we're not reading from any edges. This is the common mistake. Our eye just goes to those edges, and it's what we usually do. But we want to focus in on that 0. So go ahead and tell me in the chat box, what do you see for the whole number? Just that first step. 57's the first comment there. Anybody agree? Josie agrees. Okay, anybody else? Okay, I'm seeing some agreement, so that's a good sign. So let's just kind of count it out to prove it here. So we have the 50, of course, right here. I know this one would be 55. So here's 56, 57, and yep, it hasn't quite made it to the 58, so I can't count it. So 57 is definitely correct. And now I say point something. And I can tell it's pretty close to the 58, so it's probably going to be one of the higher decimal values. So take a look at all those dashes that come after the 0 and let me know what you think is that last digit. Okay, we're getting some agreement so far, maybe 8. You really got to get your face in front of that screen and look closely. Okay, good. So I'm going to start at 0.5. We can see that doesn't match. 0.6 is getting better. 0.7 is not too bad, but 0.8 is the first one that's perfect. Now 0.9 looks pretty good too, but we always want to take the first one that matches up perfectly. So 8 would be your correct choice there. Okay, let's try another. So the 0 is over here. Oop, and I missed it. Give that one a try. And go ahead and tell me the whole answer this time. Do the first and second and third step. Okay, Josie is suggesting 7.2. Anybody else? Okay, we're seeing a little variation here. So I'm seeing the 0.2 repeating, some 7s, some 6s. So let's talk this one through. So we have the 0 over here, which means I know I've passed 0.5, or I'm sorry, not 0.5, 5. So here's 6, and notice 7 is over here. And again, picture, that ant trying to do a mini marathon there. It's not making it past the 7. So I can't count it if the 0 hasn't passed that value. So really 6 is as far as I can take it. So those of you that said 6 for your first digit, you're right. So it's 6 point, and then again we look at those dash marks. 0.1's not too bad, but notice 0.2 is even better. So this one should be 6.2 millimeters. So it takes some getting used to, but you want to keep circling back to that 0 being the first place you read, and then looking for that digit that lines up perfectly. So I think the next thing we should do is measure from what it looks like in the lab. So this is one more practice, and what I want to also throw in is the other measurement we have to take, which is much easier. This is just a practice one, so this is not going to go in your lab, but when we do that next, you'll be reading volume, which we're just going to read from wherever that top M&M is. And it's a little hard to see in this photo. I think the background's a little yellow, and the top M&M is like right about here. So here we're not using any kind of steps like the vernier scale. We're just measuring the volume. What do you guys think that volume would be? Good. Yep. So the volume's not so bad. We're just going to read that like we would. Oh, and the dark pen doesn't work over here. 94, and this is already in centimeters cubed, so that's all you'd be entering. Again, this is just a practice though, so this one won't go into your table. Now, what we're going to look at next is the fact that these M&Ms get dumped out onto the table, and we turn them into a circle of M&Ms. And our goal here is to measure the diameter across. So the picture here at the bottom is really just to show you what the setup looks like. And of course, we're using the zoomed in one to get the actual value. So let's try this one more time. We're measuring from that 0, and we need to get that whole number. So what would our whole number be here? All right. I'm seeing the chat box move faster, so that usually is a sign that we're a little more comfortable with it. So exactly, we passed the 131, but we haven't made it to the 132. So that's as far as we can take it there, and then we have to have point something. Which dash mark matches up perfectly? Point 1, point 2 is looking close, but yep, I think point 3 is our best bet there. Now this value is in millimeters, so what you're going to have to do in the lab is convert this to centimeters, and it really is as simple as moving the decimal over one place. So if this were data we were going to put in our table, we would really have 13.13 centimeters. Anybody have any questions on those examples? It takes some getting used to, but I think after enough practice, the caliper's not as bad as it seems. So now that we have our data for volume and diameter, we need to really move on to the calculation part to this, which is finding radius and thickness. So what we need to really think back to is just the properties of a circle. We know diameter is all the way across. How do we get radius if we know diameter? What's the relationship there? Right, Chansey, exactly. We're just going to take that diameter column and divide it by 2. So you guys can go ahead and do that, and those answers will go in your radius column. So go ahead and fill those in now. We're not going to discuss those because we'll use those later when we actually plug in the calculation. So just go ahead and grab your calculator and find half of the first diameter, half of the second. Those answers will go in the radius column. Once we have that, we're going to go to this picture to help us with the calculation part. So the idea here is that, again, the purpose of all these steps is we're indirectly figuring out how thick an M&M is. In normal life, we would just directly measure it. We'd take the one M&M, we'd get our ruler, we'd measure, and we'd be done. What we're trying to do is avoid doing that and kind of get to the answer in a roundabout way. And this is the way that we can do that. So we have the volume, we also have the diameter, and those are variables that are in the cylinder equation. So if you look to the bottom of the page here, the cylinder equation is probably one you've seen in math class at some point, and we're going to try and use it in relation to these M&Ms. So I think the piece that isn't described very well in the lesson is that if we're starting with a volume in a cylinder, it would be similar to, let's say we had some Play-Doh, and it was shaped like a can of soda. That would have a certain volume, but then if we decided to flatten that out and kind of smash it down and make it into a flatter cylinder, maybe like kind of like a deep dish pizza shape, it would still have the same volume. All we've done is change the dimensions of it. So that's really what we did here with the M&Ms. We had a volume in the cylinder, but when we poured them out onto the table, they were still a cylinder. They were just a super, super, super short cylinder. So I tried to make this graphic here to show that. Notice all the M&Ms kind of from a side view technically would make a cylinder. So we know the volume. That's a number you've already put in your table. You guys just figured out the radius by taking half of the diameter. The only thing we don't know in the cylinder equation is the height of the cylinder. And that happens to be the variable that we're looking for. H will be our unknown. Now, the thing that the lesson doesn't do a very good job of telling us is that, well, this height is really very closely related to the M&M in the fact that it's really the thickness of the M&M. So what we want to be able to say is if I'm calculating for H, I'm really calculating for thickness because that truly is the thickness of the M&M from that view. So let's go back to that table. What I would suggest just making a note of, maybe either on the file or on your paper, is that technically this is the H variable in the equation. And that's really what we're going to work on next. So let's go to this area here, and this is question 1. So this is, it may even be on the same page. I had to kind of chop these to fit on the slides. But what we're going to do is rearrange this cylinder equation so that it's solved for H. So I'm going to write it a little bit bigger here on the side. V is equal to pi times r squared times H. How are we going to get H alone? Now, an average is really back to a mathematical average. So we're just going to take your two values from this table, table 1, you're going to add them together, and then you're going to divide by 2. Just like if you had 2 quiz scores and you wanted to know your average, you'd add the 2 together and divide by 2. We're doing that just to see like what's the ballpark value that our lab is giving us. So that's going to go here for average. And then, like I mentioned earlier, you're just describing what indirect measurement is. We did a whole lot of calculation, really, and we didn't have to deal with just one individual M&M. So you want to make sure you're addressing those aspects when you write up 1D. And that should take care of everything in this page. And we just have this one to go. Now there's a couple questions here. The one we already talked about, just describing what direct means, and the other is addressing table 2. Now table 2 is very brief. They're just giving us a bunch of numbers, and what the lab talks about is that someone basically did this part for us. They took a single M&M, put it in the caliper, and measured it, which is probably what we would normally do. So they did that for us, and all we have to do is take the average of those 3. So you're going to add all 3 of these together, and then you're going to divide by 3 because there are 3 data points. That average is going to go into this table. And if we backtrack to question 1C, the average that you got from the 2 is going to go over here. And the reason we're doing this is so that those numbers are right next to each other and we can kind of compare and say, okay, are these similar or are these different? After that, we'll just answer this last analysis question. So for those watching the recording, you should be able to take it from there, and you can definitely reach out to your teacher if you need additional help.